Is there another planet that's very close to Earth, kind of like us, where there could be a civilization?
Yeah, I mean, the closest star system to us, Proxima Centauri, actually has a fairly Earth-like planet around it. We don't know quite how Earth-like it is, but it's called Proxima b. Proxima Centauri b is the name of the planet. It's only a little bit larger than the Earth, and it's in the right distance away from its star that it could have liquid water on its surface. But that's about all we know about it. We just know basically its size and how far away it is. And
how do you get there? What's the freeway exit on this? Like, is there
This is 4.2 light years away.
Yes, that's a long ways route. That's not Delta Airlines or United. We got
there is an attempt to go there. So there's a project by Yuri Milner, who's a Russian billionaire. He lives in Silicon Valley now. And he's actually trying to get all the tech gurus in Silicon Valley together and scientists together to try and fund a mission called Breakthrough Starshot. I think he's put in $100 million of his own money so far into this. So he's serious. I mean, this is the biggest investment I've ever seen in something like this.
Comparable to the moon. How far is this comparable to the moon?
The moon is a few light seconds away. I think like 2 light seconds away, something like that. And this is 4 light years away. So it's 4 years divided by 2 seconds. So far, 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 far further away. Yeah.
Far further away.
Yeah. I mean, with this mission, they want to travel at 20% the speed of light, which is totally unprecedented. If you took the fastest thing so far, that's the Voyager 2 spacecraft, it would take Voyager 2 about 10,000 years at its current speed to get there. They want to get there in 20 years, right? So that's a huge speed up, a factor of 500 speed up. So to do that, you can't have a vehicle like a conventional space shuttle or a spacecraft that someone would sit inside. It will be like a nano chip, like a tiny, tiny spacecraft that will weigh like just 1 gram. It'll be stretched out into a tiny thin sail. There will be just maybe 20 or 50 atoms across, incredibly thin. And this very thin sail will be pushed by a laser beam. Now, light has pressure. We don't notice it, but this light shining in my face, it's actually slightly pushing me back at a very, very minute force. But I'm so heavy, it's not enough to move me. But if you make a very, very light, thin sail that's highly reflective, it can be pushed. So they're going to bombard that with a massive laser, gigawatt laser from the ground that will accelerate it to speeds approaching the speed of light, ideally, and then get it to fly past Proxima Centauri. It won't be able to stop there. It will just go straight past and hopefully just snap a couple of photos and then somehow, the question is how, beam that data back to the Earth so we'll have the first ever true photo of another world.
So this is not a person or group of people, as that are going to live in a whatever spaceship for 20 years to go there, see what it looks like, and either stay or come back. That's not the case.
We wish we could do that, but no one really knows how on earth you would do that. That's just complete science fiction. We don't have any propulsion system that could possibly get humanity to another star system in our lifetime.
Okay, so as of right now, how much do we know about this? What's it called? Yeah, what is it?
B.
I want to say the name right. Proxima Centauri b. How much do we know about it?
Precious little. It is around a very strange star, but also a very common star. So the star is actually the most common type of star in the universe. Is called an M dwarf, and this is what this star is. It's in a triple star system called the Alpha Centauri system. There's Alpha Centauri A and B, which are pretty close to each other. I think they're sort of the orbit of Jupiter around the sun away from each other. And then there's Proxima, which is really far out on a very wide orbit around this binary star system. And then this little star, it's very diminutive. It's about, I think, 1/8 the mass of the sun, so a very small star. You can't really make stars that much smaller than this, else they wouldn't even be stars anymore. They'd be failed stars. So it's one of the smallest stars you can have. And around this very dim red star, we find this little planet, Proxima Centauri b. We think there's actually additional planets in this system. There's probably a planet, we call the first planet that was discovered planet B, and then we go up the alphabets. The next one's C and D, and I think there's evidence for a C and a D at this point. Astronomers are still arguing about the reality of those two, but it looks like a multi-planet system with an Earth-like planet in the habitable zone, and that's about as much as we know. We don't know much about its atmosphere. We don't know about its surface. We certainly don't know about life on it. People have searched for radio signatures. They've beamed our most powerful radio telescopes and listened. Do we hear a communication? We don't see anything. It's completely silent as far as we can tell. So as far as we can tell, it's just another Earth. And probably there are a lot of Earth rocks out there. These stars, we have worries about them as being possible habitats for life, even though 3/4 of all stars in the universe are like this type of star, these red dwarfs.
3/4.
Most stars in the universe are like this guy. We're the freaks of the universe living around a sun-like star. I always think that's wild. People don't realize that. Like we live around a single star system, not a binary star system. That's already kind of odd. About half of all stars are in binary star systems. And then on top of that, we live around a yellow star, sun-like star. Only about 10% of all stars look like our own sun. And the other 75% of them, there's a big bracket below that, which look like these guys, these M-dwarf stars. These stars are amazing. They live for trillions of years. Our sun's on the way out, only has about 1 billion years left, and then the Earth will be uninhabitable. Whatever we do with climate change, whatever we do to the planet.
How much do we have left?
Less than 1 billion years.
We have less than 1 billion years.
Yeah, so the sun will not engulf us at that point. I think people normally think the sun's going to gobble up the Earth. That won't happen for about 5 billion years. But way, way before that, the sun is increasing in power. So its luminosity is growing gradually over time. It's already increased by 30% in the last 4 billion years. So it's already been growing in power significantly. If it gets much more powerful than it currently is, it'll tip us out of the habitable zone altogether, irrespective of what we do on this planet, human beings. So even if humans are long gone, Earth will still be pushed out of the habitable zone in about 1 billion years. So when that happens, maybe Mars might become habitable for a short while as the sun continues to warm. But it really is kind of an end point, you might think, to life in this solar system. Whereas these stars, these M-dwarf stars, they can go for trillions of years. That's far older than the current age of the universe. And so I think it's a mystery. I call this the red sky paradox. How come we don't live around one of these stars? There's more of them. They seem to have more Earths around them, as far as we can tell, than sun-like stars, and they live far, far longer. So that seems like they've got everything going for them. And therefore, it's kind of interesting and perplexing as to why when we look up in the sky, we don't see a red sky, as I call it, like the red star.
Let me ask you, how do you know these stars live for trillions of years?
That's a good question. So obviously, no one's empirically observed that to be true because the universe is only 14 billion years old, 13.8 billion years old. So we think this to be true based off our understanding of stellar theory. We certainly know when stars eventually die, stars like the sun, it will eventually become a white dwarf star. Stars which are more massive will become black holes or neutron stars. And so when we look at all the dead stars that we see out there, we can kind of figure out how heavy it used to be before it died. And we know that there are no red dwarfs which have ever died yet. We don't see any stars which look like the remnants of a red dwarf star. So certainly we know for sure they live for a very long time. The reason why we think they live for a very long time is because their luminosity is it's like the candle that burns half as bright burns twice as long.
Candle that burns half as bright burns twice as long.
Yeah.
Okay.
Right? Because there's a certain amount of wax.
Makes sense.
There's a certain amount of fuel.
Right.
And if it's only, just a tiny little flame on
Makes
there,
sense, yeah.
it's going to take a long time to churn
That's a
through
good visual
all
to
of
be
that
thinking
fuel.
about. Yeah.
So these stars, they actually have a huge amount of mass. They're about 10% the mass of the sun. So they have a huge amount of hydrogen to burn through. But their luminosity is not 1/10 of the sun. Their luminosity is like 100th or even 1,000th that of the sun. So they're very, very dim. And because of that, they take a long time to burn through their fuel. They're also extremely efficient. Unlike the sun, they have convection all the way through into their core. So, like in your tank of water in your home that turns over and heats the water in your house, there's a convection cycle. So as you put a heater at the bottom, you'll get hot water at the bottom of the tank. It will then rise because hot stuff expands like a hot air balloon. It will expand, it will float to the top, and then it will get cooler and it will sink back down to the bottom. Now in the sun, that doesn't happen. That only happens basically at the very top of the atmosphere. When you're close to the core of the sun, it's producing so much energy. It's like a nuclear furnace that's just blasting out in your face, and nothing can sink down because the power coming out is just too intense. So we call it the radiative zone. But these stars, they're so dim that everything can churn. And because they can churn, they get to gobble up every last hydrogen atom if they want to, or very close to. All the hydrogen in the star, they can use over time. So that's why we think they should last for trillions of years.
So if we rely on the sun, what do they rely on?
Well, the planet around the red dwarf, you mean?
Yes.
For their energy source, they would just have to be closer to the star to get enough energy.
They would have to be closer to the sun?
To their sun.
To their sun.
Yeah, which is this red dwarf star. So that's why this planet is actually much closer in than Mercury is around the sun. It's very, very Proxima Centauri b.
How many suns or red dwarf planets, how many of those are out there?
In the Milky Way, there's about 100 billion stars, and there's about 3/4 of those, so 700, 0.75 of that is essentially 75 billion red dwarf stars we would estimate to be in the Milky
Like
Way.
a sun.
Yeah, but they're not all catalogued. We just think that like the sun, there's probably about 10 billion.
Oh, like the sun, there's 10
So let's say
billion.
10 billion suns,
Yeah.
75 billion red dwarfs. But to be clear, we haven't catalogued all those stars. Those are just estimates.
So right now, when we look out, what do you call it? When you're sitting outside and you're looking out what are the tools you guys use?
Telescopes.
Telescope.
Yeah.
How far out is the most advanced telescope today?
In terms of how far out can it see?
How far out can it see?
You're probably talking about JWST for that. So JWST, the James Webb Space Telescope, is this, NASA's latest toy.
That's the one?
Yeah, it's the successor to the Hubble Space Telescope, launched a few years ago. I myself am using it in October, which I'm very excited about.
You've never used it before?
Not yet.
Okay. What's special about it?
It's massive. It's 6.5 meters in diameter, so it's the largest space telescope we have. It's also an infrared telescope, so instead of seeing invisible light, it sees in heat, essentially. And the beautiful thing about that is it can penetrate through dust. So visible light gets blocked by dust, and in space there is a diffuse cloud of dust that kind of obscures your vision. But if you look in infrared light, you can just peer straight through it and go all the way to the other side of the universe. So this thing is seeing galaxies which are in the process of forming. And so we are seeing galaxies that are of order of 100, 200 million years old, which is that's 0.1 billion years old, and the entire universe is 13.8. So this is a tiny, tiny fraction. I guess the furthest we can see back in total is actually not from this telescope at all, but would be what we'd call the cosmic microwave background, or CMB. That's a useful thing to check out. If you can Google that, you'll see this this beautiful picture of like dots, which is again like there we go. So this is taken in millimeter and radio wavelengths. And this is light, which has traveled for 13.8 billion years and is just reaching our telescopes, the light that you're seeing in this image. And so it left whatever was emitting it was basically a cloud of dust and material when the universe was 380,000 years old. So this is the oldest light we can see. It's actually impossible to see light before this point, because before that point, the universe wasn't transparent. It was opaque. Before this point, there were no atoms. So protons and electrons were not bound to each other. And so light just couldn't even travel through the universe before that point. So it's never possible to see light before that point.
Why is this important to astrophysicists?
Oh, this is a hugely important image. It teaches us about the origins of the universe. It's one of our strongest evidences for what we call, essentially the Big Bang Theory, the origin, understanding how much dark energy there is, dark matter there is. It's a fascinating thing about it is that it's so homogeneous. And that has been it was a puzzle for a long time. So these little differences you see in the image, if you scroll down a tiny bit there on that image, they're tiny. So this whole thing, all the light is about...
What's the red represent?
Hotter regions, and the blue is colder regions. So the
yellow is whatever intermediate?
In between.
Okay,
yeah. So this whole image is about 2.7 Kelvin. So very close to absolute zero. Very, very cold light that you're seeing here. When it was emitted, it was very hot light. But simply the expansion of the universe itself has cooled it down over time. Now, the differences here are tiny. I can't remember the exact number. We're talking like millikelvin, microkelvin differences between these regions. And those hot regions, they're slightly denser, and the blue regions are slightly colder. And so these differences, the over-densities, are what gave birth to galaxies. If this was completely smooth, and we didn't see any differences here, then you wouldn't have stars, you wouldn't have galaxies. It's the fact that you get slight over-densities in different regions.
This is shown what? This is shown all of the galaxy? Or what is this showing?
That's the whole universe.
That's the whole universe?
That's the whole sky.
That's the whole sky?
Yeah.
And okay, so...
That's the whole universe in a single image. Just
so if that's the case, what's the end?
What do you
is
mean by
there
the
an end? Because the way this shows, there's an end to a universe, no?
There's no end. This is a wraparound image. So this is like your full sky. You imagine like you do like your 360 camera.
But is there an end?
We don't think so. As far as we can tell, the universe just goes on and on and on in every direction. So it does seem, we can actually measure from this image, you can actually measure the curvature of space itself. And so an open question is, if there was a wraparound universe, you could travel in one direction in a spaceship and you'd eventually come back to the same position. So the universe could be like a big sphere, like the Earth is, like a big sphere, but in like a hyperspace kind of dimension. Now, when we look at this, we don't see any curvature. As far as we can tell, the universe is completely flat, very, very, very flat. Now, that is consistent with a universe that just goes on forever and ever in all directions. Perhaps there is an end like this table has, like it
We
just
don't
suddenly
know.
cuts off.
We don't know.
But we don't see it.
Okay,
As far as we can tell, everything we can see, it just goes on and on and on.
So let me ask you a question. This telescope I just looked at, is it true that the cost to make it, Rob, I sent you a link, was $10 billion?
Yeah, unfortunately, it was when it was first projected to be built, it was, I think, $500 million. Ended up overrunning by a factor of 20 in cost and 16 years in launch date.
16 years it took to build it.
No. It took longer than that. It was
launch date.
It was originally supposed to launch 16 years prior to when it did launch.
Got it.
So it was massively set back, both in terms of cost and
Who gets
date.
to use this? Who gets to go?
Anyone. You could use it. So you can write a proposal to NASA. There's a cycle coming up October 25th, I think the date is coming up. You just, if you want to, you just Google, if you want to, JWST Cycle 4. That's what to search for, JWST Cycle 4. And then you can write a proposal.
In these uncertain times, if there's anything we need people to believe the future looks bright. So if you've heard about me saying this mission to you, we're on a mission to get 1 million people to wear this gear. And this is what we're doing. If you buy one of these hats, there's a category of buying one hat, getting the second one free. If you haven't yet worn this gear publicly, go ahead and test it out. Buy some of the gear, wear it in public, and see how many people will stop by and say, you also watch Valuetainment? You also follow PBD Podcast? I do too. Place your order. Go to vtmerch.com, click on the link above or below, place your order, and represent the VT and the PBD Podcast gear.
So if you like this clip and you want to watch another one, click right here. And if you want to watch the entire podcast, click right here.